Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem profitable schemes. We're given several parameters here. One is a group of members. So each value in this array is going to represent how many members are in each group. So this one has 2, this one also has 2. We're given a second array profits where each value represents the profit from a scheme. Now these two arrays are related, meaning that for this scheme we get a profit of 2, but it takes us 2 group members for us to actually get that profit. And for this next one, we can get a profit of 3, but it takes us again 2 members to get that profit. And the thing is, we are given a limited quantity of group members. That is what the N value stands for. So in total, we have 5 group members, even though in this array, if you total it up, it's actually 4, which basically means that we are allowed to do every single one of these schemes. We're left with a total profit of 5. We are then left with a single group member, which doesn't really matter because we can't do anything else with that group member. And the question is not how big of a profit we could get. In this case, that would be 5. The question is how many ways can we generate a profit that's greater than or equal to another parameter that we're given, which is the minimum profit. So how many ways can we get a profit from this array while not going over the threshold of group members? How many times can we do it that leads to a profit greater than 3? The first thing to probably try with this problem is just try to brute force it, see if there's anything that we can do using backtracking, and maybe if there's a way that we can optimize that backtracking, we can come up with a dynamic programming solution, which is the case for this problem. So I'll quickly go through the memoization solution after we do the brute force approach, but then I want to show you how we can do the tabulized, like the formal dynamic programming bottom up approach. There are going to be 3 dimensions in this case, so I'm going to try to run through it quickly. And while it is challenging, I think this isn't too crazy for a hard problem. It definitely is if you're new to these concepts like backtracking and dynamic programming, but it's mostly logical. So I'll go through kind of the relationship here. We have to think about it in terms of what choices can we make? How can we make the choices intelligently to go through every single possibility, but also make it as efficient as possible? So when we start out, we start with n equals 5 people. It could be a different number, but that's a variable we start out with. We have 5 total people. We also have a current profit. Let's call that P. And initially we'll say it's 0 because initially we don't have any profit, but we are trying to make decisions. We're going to backtrack to get us to all possibilities where our profit is greater than that minimum profit, which was 3. Now there's a third parameter we have. It's going to be I in our recursive function. It's going to be initially 0. It's going to tell us the index that we're at in our group and profit arrays. So let me tell you, what is our choice when we start at the first scheme, which generates a profit of 2? What's our choice here? Well, we can either choose this scheme or skip this scheme. So this problem is very reminiscent of the 0-1 knapsack problem. You can tell that it is leading us down the dynamic programming path. And I've covered this pattern extensively on my website, leetcode.io. The general idea is that for each of these values, and this is actually a bit different than the 0-1 knapsack because we're not like counting ways and things like that. This is getting us to the maximum profit. So it's a bit different than like the coin change problem. Other than that, it is very similar. So we have a choice to take that profit, which will give us a total profit of 2. N will then be subtracted by 2 because it took 2 group members to get us here. But we end up at N equals 3, P equals 2, and I equals 1. We're at the next position in the array. But if we skip the first value, our first 2 parameters stay the same. We still have 5 people. We still have a profit of 0. And now we are at I equals 1. We went to the next position without taking this scheme, the first one. And ultimately, this is how our decision is going to work. You can tell that both of these paths will never lead to duplicates, because if in this path we took the first profit and in this one we skip it, well, none of these children are ever going to be the same, because in this one we'll always have the first scheme and this one will never have the first scheme, because if we skip it, we're never going to come back to it. Now, all that's really left for us is to figure out what the base cases are. One is kind of obvious. We run out of people. N is less than or equal to 0. We have no more people left, so we can't keep making choices. So then the question is, did we exceed the minimum profit or reach the minimum profit? And we would know that by comparing our p-value with the minimum profit. So this is a base case that might end up returning 1 if it is a valid way to exceed the profit, the minimum profit, or it might end up returning 0 if we did not exceed the minimum profit. Another base case is if we run out of profits to choose from, if our I index goes out of bounds. In that case, we would do the same thing. We would check, is our current total profit greater than or equal to the minimum profit? So those are our two base cases. Either this goes out of bounds or this goes out of bounds. This becomes less than or equal to 0. This becomes too large. Now, if our profit exceeds the minimum profit, we don't really care because we're trying to generate all possible ways where we can do that. So if going down these paths, this exceeds the profit and this exceeds the profit, we're still going to keep making decisions because we want to count the total number of ways we can exceed the profit. So that's how we would solve this problem with backtracking. We can take all three parameters for our recursive function and apply memoization, which will give us an optimal time complexity approach where the time complexity is going to be n multiplied by the length of the group, which is the same as the length of profit. Let's call that m. And also the minimum profit, because I'm running out of variables, let's call that p. So this would be the overall time complexity of this approach. So now let's code it up. So once again, I didn't really mention that our result could be really large. So we are going to want to mod it by a constant value, which is usually this 10 to the power of 9 plus 7. It's a really large prime number. So then we're going to start with our recursive function, taking in the parameters I mentioned. I is going to be the index we're at. N is going to be how many group members we have left, and P is going to be our current profit. We know that the main base case here is if we reach out of bounds, so I is going to be too big, it's going to be equal to the length of the group, in which case we're going to return 1 if our profit exceeds or is equal to the minimum threshold, otherwise we're going to return 0. Now technically there is a second base case I talked about, but we're going to address that a little bit differently. So we know there's two choices now, the recursive cases. One is the simple one where we skip the current value. We call DFS on I plus 1, but we leave N the same. We still have the same number of group members and we still have the same profit because we skipped the current heist. So I'll just say skipped index I. The other case is if we do not skip index I. So we still go to the next index, but now our number of group members is going to be different because we decided to take the profit at index I. So now our number of group members is going to have decreased. It's going to be N minus the number of group members at index I. The thing I always mess up is I always have like a plural here. I always end up with S's. So if you see me doing that, please ignore it because I'm pretty sure I will mess up at some point, but that's how we're going to update the number of group members. Now you tell me, how do we update our current profit? It was P, but we have to add to it now. We have to add to it the value at index I in the profit array. So let's do plus profit at index I. The thing is, when we call this DFS, it's possible that this is not a valid thing for us to do. What happens if our N now, our number of group members, became negative? How about we just wrap this in an if statement to make sure that's not going to be the case? So N minus the number of group members at index I has to be greater than or equal to 0 for this to be a valid move. Whoops, didn't mean to get rid of it. But now we have this wrapped. So these are the two cases, the recursive cases we can do. Now, how do we add caching to this solution? Well, it's pretty easy, especially in Python where you can just use like a hash map for everything. I'm going to call it DP. It's going to be a hash map where the key is going to be these three values. You can tell by how I'm about to use it. So DP is going to be how we eliminate repeated work. If we call this function multiple times with the exact same parameters, we don't want to have to go through all the recursion to get the exact same values. So we're going to store the value in a hash map, which I'm doing here. The key for the hash map is going to be I, N, and P. It's usually always the parameters of your recursive function. So that's what I'm doing here. This is the initial value we're giving it. And then if this if statement executes, we want to add to the value that we have stored here. But don't forget, we always want to mod by this value. So that's what I'm going to do over here, mod by that constant value. And then we want to return the DP value that we have stored here. And lastly, don't forget to always add another base case. What happens if this has already been computed? We don't want to go through all this work again. So what we're going to say is if this tuple is in our DP cache, then just go ahead and return the value we have stored there and don't go through the recursion. And then here, we're going to call our DFS with the parameters where index is going to be 0, n is going to be the parameter n, and p is going to initially be 0. Now, if I try to run this, this is actually going to give us a time limit exceeded error. Maybe if you change this, instead of being a hash map, making it a 2-dimensional or rather 3-dimensional array will pass on Leetcode. Or you can go with the tabulized approach, which usually is the same overall big O time complexity, but it usually runs a bit faster and gets accepted on Leetcode. So let's go code that solution up. So I'm going to do that right now, right here. The idea is that instead of solving this problem recursively, which is usually considered top down, we're going to solve this bottom up, which is basically to say we're going to compute all the values that we're storing in this DP hash map, or really it's a 3-dimensional array. We're going to compute those values in an intelligent order so that we don't do any repeated work. So the time complexity will overall be the same. It's just that running it without recursion is less overhead, so it ends up running faster. But we're going to, again, in this solution, have a hash map, but I'm going to call it a default dict, and I'm going to give it a default value of an integer. It's usually easier to do it this way because you don't actually have to initialize that 3-dimensional array, which is kind of a pain and it's just a bunch of boilerplate. But usually if you use the recursive solution as a template, coding up the actual dynamic programming solution isn't too bad. It's just kind of tricky to get your head around it. First, I'm going to show you how it's going to work, and then I'm going to show you a few of the edge cases, sort of. We want to have 3 loops here because those are our dimensions here. So for the first loop, I'm going to say for I in range length of the number of groups we have. And then I'm going to have another loop for member. So this is the member count in range of n, and I'm actually going to call this m for short, but it stands for members. But trust me, you don't want long variable names in dynamic programming solutions because it gets even harder to read, in my opinion. The third loop we're going to have is, of course, for p for profits. So what range do we want that to go through, though? Because it's not super obvious. We want it to be from 0, let's say, up until the minimum profit, which we don't really need a 0 for. This should sort of hint to you that we probably want a +1 here, because when we calculate a value like in this DP hash map, or you could call it a 3D array, when we have a value IMP, we want this to map to the number of ways we can generate profitable schemes with these parameters. So basically, this is a sub problem. What does I stand for in the sub problem? If we have an array of groups, let's say they're 1, 2, 3, if I'm at the first index of groups, what subproblem does that mean? Does that mean we're talking about profitable schemes only in this portion of the array? If I was at index 2, would that mean this portion of the array, or are we talking about this portion of the array, the prefix or the postfix? Well, it's kind of your decision how you want to set up the dynamic programming problem. I usually try to do it in a way that the recurrence relation is similar to the recursive solution that I have here. So basically, the recurrence relation is how we call our recursive function. We see that the two choices here are skipping index I and including index I. So I want to code it up a similar way. So what I'm going to do is have my index go in reverse order. So when my index is over here, I want it to be talking about this subproblem. If we only had these values, what are the profitable schemes we could do? And when my index is here, I want it to be talking about this portion of the array. So I'm going to have my index iterate in reverse order. You can do that like this in Python, starting at length -1 and then going in reverse order. And since these are our parameters, we probably want the number of members to stop at the total number of members that we have. We want it to stop at n. The way this is coded up, it's going to stop at n-1. So let's change this to n+1, and the profit should be changed to profit +1. Now, before we start thinking too much about the edge cases, what's the overall code here going to be? We know dp here, our parameters are going to be I, M, and P, just like we have here. So for this subproblem, we're asking how many ways can we generate profitable schemes on this subproblem. We know what the I means. It tells us which profits we can choose from. M basically means how many members we currently have, because we don't want to have more than n members. So this is how many members we currently have, and P is going to tell us what our current profit happens to be. So similar to how we set it up with this DFS. And the value we're going to assign here initially is going to be the exact same that we did down here. Initially, this is going to be set to the value that's stored at I+1, keeping all other parameters the same. The other case, as you might guess, is also going to be similar to down here. I could almost just copy and paste it. In fact, I think I will, to show you what we're going to be changing here. So here we want dp of the same key that we have up above, I, M, and P. We want to add to that this value down here, but we're not going to be calling it recursively. So let's get rid of the DFS. This is going to be the key of our hash map. We are going to say I+1, but now our number of group members is going to be different. We have M group numbers. For the recursive solution, we were subtracting because that's how we were keeping track of like our current group members. But for this, we're going to be adding, because that's sort of the way we've set this solution up. When we read from our DP cache, we want to read for how many members we have remaining now. And to get that, we need to take our current number of members and add to it the number of members we have in the ith group. So here I'm going to change this to M plus the value at group index I. And for P, we're going to be doing the same thing that we were doing below. We're going to add to the profit, but there is a small change we're going to make. I'll show you in a second. The first question is, what happens if M plus the number of group members we added is too big? Well, for that, let's make sure it's not too big. Let's make sure M plus group at index I is less than or equal to the threshold, which was N. So that's one check. Now, the second check is, what if our profit is too big? Well, it's never going to be too small. It's starting at 0 and we're only adding to it. But what if it exceeds the minimum profit? Well, remember what we said, we're trying to generate the number of ways. So just because this is a way to exceed the minimum profit doesn't mean we have to stop. If we exceed the profit, we don't have to stop. That's the number one most important thing. The second thing is, what do we do? Because we want to count the number of ways we exceed the profit. So if one of the ways does exceed the minimum profit, well, in that case, we'll just take the minimum. So we'll take minimum of the minimum profit and whatever profit we calculated. So this way we will not go out of bounds. Well, we have a hash map, so we can't really go out of bounds, but basically we want to use the same key value regardless of whether we went over the profit or we exactly reached the minimum profit. This is probably the trickiest part, I think, to come up, and it's really hard to visualize as well. So you kind of need some intuition with these types of dynamic programming problems. But don't worry, we're almost done here. We didn't forget that divide by mod. The way we are coding this up, the value will be stored in the origin of our DP hash map. But if you don't remember, you can always just say dp.values and then take the max of that. I guess this might be a bit more simple, so that's what I'll keep for now. But the last thing before we can actually run this code is, what about the base case? With recursion, the base case is simple and pretty intuitive, but with dynamic programming, we have to initialize our cache, our grid, to account for the base case. And in this case, the base case, we can handle like this. For I in range n+1, the reason I'm taking I is because it's the variable that's not going to change when we execute this line of code. Here for DP, I want to use the key which corresponds to our base case down here, where I is equal to the length of the group. That's the base case. So I'm going to use the same thing here. I'm going to get the length of the group as my first key. And the second key is if P is greater than or equal to the minimum profit, then return 1. Otherwise, return 0. By default, this hash map is going to return 0 for all values that we don't have stored. Like if we use a key value that isn't stored here, we will return 0. So we want this to return 1 when our profit is greater than or equal to the minimum. So that's our third key. I'm going to use minimum profit as the variable for that, because I explained what we're going to do when this minimum profit exceeds the threshold. We're just taking the minimum here anyway, so it never will exceed that threshold. And lastly, what was the third value that went here? It was I, which in this case, it's a bit misleading because I is supposed to be the first one, but this really just counts for how many group members we have. So to make it easy, I'll just change it to M. So put an M over here, so you know that this M is the same one that corresponds to this. But now let's go ahead and run it. But let me tell you what we're going to do here. We're going to set a 1 value here because this is our base case. This is the case where we would want to return 1, just like we did in the recursive solution. So now let's run this to make sure that it works. I think I just forgot a backslash here, so Python is complaining, but let me rerun that. And as you can see, yes, it does work. I will quickly mention that I'm pretty sure the time complexity is so low because we're using a hash map, and usually it's a lot faster to just use like a multi-dimensional array because you don't actually need to do the hashing operations on each like assignment that we're doing. And also I forgot to mod the answer by the mod that was making me fail a test case. So I wanted to mention that in case anyone else runs into it. But if you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. It has a ton of free resources to help you prepare. Thanks for watching, and hopefully I'll see you pretty soon.